Today we are going to discuss a new concept in special relativity. Actually, this concept was developed by a great mathematician, Minkowski. And this is actually the concept of four-dimensional formulation of our space. In fact, in earlier lecture, in the beginning of special relativity, you have learnt about Lorentz transformation. And that Lorentz transformation actually gives a very important idea about the dimension of our space. When you have studied the classical relativity, that is the Newtonian relativity, you can say, and you have seen that the classical relativity is based on a transformation law which is actually called Galilean transformation. Okay, and in Galilean transformation you have seen that the space and time are independent from one another. It means the space coordinate x, y, z and the time coordinate t are independent from each other. Okay, you have seen that the Galilean transformation was x prime equal to x minus vt, y prime equal to y, z prime equal to z, and t prime equal to t. These are actually the Galilean transformations. And so this time coordinate is completely independent of the space coordinate x, y, z. But on the basis of the two postulates of special relativity given by Albert Einstein, we have derived another set of transformation equations which are actually called Lorentz transformations. And in that Lorentz transformation, you have seen that the space and time coordinates are not independent from one another. Actually, we will see the Lorentz transformation. You can remember it. You have already studied it. And then you will see that the transformation equations, which are called Lorentz transformations, that imply that the time in a coordinate system or in one inertial system depends on both the space and time coordinates of the another coordinate system. So to clarify this idea, let us see this figure. Actually, in this figure, I have shown two inertial systems. First one is S, you can see here, and its coordinate axes are OX, OY, and OZ. And the another coordinate system I have considered is S prime. And the x-axis of both of these coordinates coincide, and we consider that this coordinate system or this inertial frame S prime is moving with a uniform velocity v in positive x direction relative to the inertial frame S we have considered. Now let us consider that in a space at this point P, an event takes place. And you know, an event is specified by the space and time coordinate. So let us consider that the event taking place at this point P is specified in frame S by the coordinates x, y, z. These are actually the space coordinate, and time t. It means the observer of frame S finds that an event is taking place at a point P whose space coordinates are x, y, z, and the event takes place at a time t. Okay? And if the same event is observed by the observer of another inertial frame, let us say S prime, which is moving with uniform velocity v in positive x direction with respect to S, the observer of this inertial frame S prime specifies the same event by these coordinates x prime, y prime, z prime, and t prime. Okay, it means relative to frame S prime, the space coordinate of this point P are x prime, y prime, and z prime, and the event takes place at this at time t prime in frame S prime. According to Galilean transformation, both of these time will be same. But as we have learnt on the basis of two postulates of special relativity, that is the postulate of constancy of speed of light in free space and the invariance of basic laws of physics in inertial frames, you have learnt earlier in special relativity the Lorentz transformation, and actually that Lorentz transformation connect the space and time coordinate of an event in one inertial frame to the space and time coordinate of the same event in another coordinate system. And what are these Lorentz transformation you have learnt in earlier lectures. Now here I am writing these transformation equations directly. You can see the first transformation equation is x prime equal to gamma times x minus vt. Okay, you know this gamma is actually equal to what? This gamma is equal to 1 over root over 1 minus beta square. Here beta means v over c. Okay, c is the speed of light in free space. Okay, so this is the first Lorentz transformation, and the another transformation equation is y prime equal to y, the third one is z prime equal to z, and t prime is equal to gamma times t minus v over c square times x. I hope you can remember this these transformation equations, because you have learnt these transformations and its applications in very detail in the previous lectures on special relativity. Okay, and if you write the inverse Lorentz transformation, what you do? Actually, for writing the inverse Lorentz transformation, we simply replaces the primed quantities, primed variable by unprimed variable, and v is replaced by minus v. So after that you get the inverse Lorentz transformation, and that inverse Lorentz transformation will be what? This is x equal to gamma times x prime plus vt prime, y equal to y prime, z equal to z prime, and t equal to gamma times t prime plus v over c square x prime. These are the Lorentz transformation. Now from these equations, either from equation 1 or equation 2, you can see the time coordinate t prime, which is measured in frame S prime. You can see it depends on the time coordinate t measured in frame S and the position coordinate or space coordinate x measured in frame S. So you can say that t prime is dependent on t and x, which are actually the time coordinate of the event in another coordinate system or another inertial frame. Similarly, you can see this t, which is the time of an event measured from the frame S, is dependent on t prime and x prime. So we simply say that the time coordinate of one inertial system depends on both the space and time coordinate of another system. Okay, so you can say here that this t prime is just a function of x and t. Okay, and here you can say that this t is a function. Let us say the function is denoted by g. This is a function of t prime and x prime. Okay, so these transformation equations actually give a very important idea that the space and time coordinate are not completely independent from one another. So you can say, instead of treating the space and time coordinates separately, it is very natural to seek the way so that both the coordinates are dealt together similarly. Okay? In fact, this idea forced Minkowski to imagine a space where time is taken just as a space coordinate. Time is not treated as in fact independent from space. Okay, so Minkowski was the first to develop a procedure in which the time coordinate is treated similar to the three space coordinates. Okay, and when we consider that the time coordinate is just similar to the space coordinate, then the space will be actually four-dimensional space, which is called Minkowski space. That space is also called world space or the space-time continuum, or simply we also say that space as a four space. In fact, what I have just explained, I have mentioned it here. You can say that in relativistic mechanics, the space and time coordinate depend on each other. Okay, already I have explained it, and you have seen that this t prime is just a function of t and x, and t is a function of t prime and x prime. Okay, so I have told you just now that the time coordinate of one inertial system depends on both the space and time coordinate of the another system. Okay, and that's why I have told that this idea forced Minkowski to think about a space where time and space are not independent from one another. And so Minkowski talked about space-time instead of space and time. Mark it. When you say space-time, it means space and time are not independent from one another. And when you say space and time, that means space and time are independent from one another. So Minkowski found an idea from this Lorentz transformation that the space should be think about as a space-time, not a space and time. Okay. Now, actually, when we treat the time as the fourth coordinate, what should be its form? Actually, this fact I have dealt in very detail in my lectures or in my videos on relativistic electrodynamics. You can go through the playlist of my channel and open the videos on relativistic electrodynamics, and definitely you have studied those things. There you will find I have solved actually three problems. I am talking about only two problems here, but if you want to see the details of this idea, definitely you should watch my video on relativistic electrodynamics. Okay. In fact, there you will find that the space interval, if you consider a point, let us say O, whose coordinates are 0, 0 and 0. This is just origin. And another point P, whose coordinates are x, y and z. Then you know that distance between these two points, if you denote that distance s, then that s will be equal, that s square will be equal to what? That will be x square plus y square plus z square. From distance formula you have learnt in coordinate geometry, this is x minus 0 whole square plus y minus 0 whole square plus z minus 0 whole square, and that will be simply equal to x square plus y square plus z square. Okay, this is called a space interval. If you will watch my video on relativistic electrodynamics on this problem, you will find that it is found that this space interval, which is just a three-dimensional formula, is not invariant under Lorentz transformation. It is not invariant. When you say that it is not invariant, what does it mean? It means if the coordinates of these points in the another coordinate system, let us say, are x prime, y prime and z prime, then it is found that this is not equal to x prime square plus y prime square plus z prime square. Okay, it means x square plus y square plus z square is not equal to x prime square y prime square plus z prime square. Okay, so we in accordance with the Lorentz transformation, so we simply say that this space interval is not invariant under Lorentz transformation. Okay, I have actually mentioned it here that for proof you can see my video on relativistic electrodynamics. Actually in that video you will find the proof of this. Okay, you can go through that video to clarify this idea. I have just mentioned the information here. But when we talk about the space-time interval instead of space interval, if you are talking about the space-time interval, that space-time interval is defined like this. This is x square plus y square plus z square minus c square t square. Then it is found that this space-time interval is invariant under Lorentz transformation. Okay, when you say that it is invariant under Lorentz transformation, what does it mean? It means that this x square plus y square plus z square minus c square t square, this is equal to x prime square plus y prime square plus z prime square minus c square t prime square. Mark this, c will remain same. This is actually the second postulate of special relativity. C, that is speed of light in free space, is same in all inertial system. So what you have, what you are seeing here, this three-dimensional formula, which is actually for the space interval, that is x square plus y square plus z square, it is not invariant under Lorentz transformation. But when we talk about the space-time interval, which is defined like x square plus y square plus z square minus c square t square, then it is found from Lorentz transformation that it is equal to x prime square plus y prime square plus z prime square minus c square t prime square. It means a space-time interval is same, is equal, are equal in both the inertial systems. Okay, so we simply say that the space-time interval is invariant under Lorentz transformation. Okay, actually in my videos on relativistic electrodynamics, you will also find another very important problem. You will see there that the Laplacian operator del square, which is defined in Cartesian coordinate like this, del 2 by del x square plus del 2 by del y square plus del 2 by del z square. This operator is also not invariant under Lorentz transformation. When you say that this is not invariant in Lorentz transformation operator, what does it mean? It means this is not equal to del 2 by del x prime square plus del 2 by del y prime square plus del 2 by del z prime square. Del z prime square. It is not equal. But when you talk about a four-dimensional operator which is called D'Alembertian operator, or it is also called box operator, then you will see that this box operator, which is defined in frame S like this, box square equal to del 2 by del x square plus del 2 by del y square plus del 2 by del z square minus 1 over c square del 2 by del t square. This is called D'Alembertian operator. You will see in my video on relativistic electrodynamics, I have proved this result, that this operator remains same in both of the inertial systems. That is, box operator or D'Alembertian operator is equal in inertial frame S and also in inertial frame S prime. It means this is equal to del 2 by del x prime square plus del 2 by del y prime square plus del 2 by del z prime square minus 1 over c square del 2 by del t prime square. Okay, del t prime square. Okay. So we simply say that Laplacian operator is not invariant under Lorentz transformation. It means its value are different in different inertial system, but the D'Alembert operator is invariant under Lorentz transformation. Actually, getting idea from these results, Minkowski thought about a four-dimensional Cartesian space, and actually in that four-dimensional Cartesian space the positions are specified by x, y, z or x1, x2, x3. It means instead of x you may write x1, instead of y you may write x2, instead of z you may write x3. Okay. Now, as you have seen that this space-time interval, that is x square plus y square plus z square minus c square t square, it is invariant or covariant under the Lorentz transformation. You can also see that this D'Alembert operator is also invariant under the Lorentz transformation. Actually, the form of these two formula implies that what will be the fourth coordinate. Actually, on the basis of these two formula, Minkowski suggested that the fourth coordinate should be taken as ICT. Fourth coordinate should be taken as ICT, where actually this I stands for the imaginary, which means a square root of minus 1. Okay. If you will write the fourth coordinate as ICT, these formula will valid. Okay. And that's why in this four-dimensional space, which is actually called Minkowski space, and as I have told you earlier, this space is also known as four space or world space or space-time continuum. There are several names of this four-dimensional space. In this space, now we write the four coordinates by these symbols. x1 means x, y is written as x2, z is written as x3, and this ICT is written as x4. So in this four-dimensional space, if an event is to be specified, now you can specify the event by a position vector like this: x1, x2, this is x2, x1, x2, x3, x4. Or instead of this x1, x2, x3, you can write vector r. Okay, this is actually the position vector in three-dimensional space, and instead of this x4 you can write ICT. Actually, in this condition, this position vector or radius vector is also called four radius vector. It is called four radius vector or four position vector. We will see in the next video the concept of the four vector. Already we have described this four vector while studying the relativistic electrodynamics, but again here we will see the concept of this four vector. Okay. So how you will specify an event in four-dimensional space? In four-dimensional space, we specify this any event by a position vector whose components are x1, x2, x3, and x4, where x4 means ICT, and these x1, x2, x3 stands for the position vector r in 3D space. Okay. Now, getting the idea of this Minkowski four-dimensional space, we will now write again the Lorentz transformation in terms of this fourth coordinate, that which is denoted by x4 or ICT. Okay. Now see, here the first Lorentz transformation we have seen, this is uh, x prime equal to x minus vt over 1 minus v square by c square's square root. Now you have learned that instead of x, now we will write x1. So the first Lorentz transformation is now written as x1 prime equal to x1 minus vt over root over 1 minus v square over c square. Now, instead of this v by c, you can write beta. So this equation may be equivalently written as x1 minus vt over square root of 1 minus beta square. But as you know that 1 over root over 1 minus beta square is equal to gamma, this is actually called Lorentz factor. Gamma is called Lorentz factor. So this this may be written as gamma times x1 minus vt. Now here as you know that x4 is equal to ICT. x4 equal to ICT. So what will be t? T will be equal to x4 divided by IC. Because now our aim is to write the Lorentz transformation in terms of the fourth coordinate denoted by the symbol x4. So this t is replaced by x4 divided by IC. Okay. So I have replaced it. Now you can see this 1 over I. You know this 1 over I is equal to minus I. So 1 over, instead of 1 over I, we will write minus I. Minus is already present here. So this will be plus I. Okay. And again, you know that V over C is beta. So instead of V by C, we have written here beta. So our first Lorentz transformation in terms of the fourth coordinate denoted by the symbol x4, you can write x1 prime equal to gamma times x1 plus I beta x4. I think we have understand. Okay. This is just the Lorentz transformation, but we have written x4 instead of t here. Okay. The second Lorentz transformation you know is y prime equal to y. So instead of y prime, we will now write x2 prime. So x2 prime is equal to x2. Similarly, z prime is written as x3 prime. So x3 prime is equal to x3. And now if you remember the fourth Lorentz transformation, that was t prime equal to t times gamma into t minus b over c square into x. Here I have written x4 prime, and you know x4 prime is will be ICT prime. x4 prime will be equal to ICT prime because x4 is ICT, so x4 prime will be ICT prime. But according to Lorentz transformation, what is this t prime? This t prime is equal to this much. You know it. Okay. So here I have written IC times, and instead of t prime, we write gamma times t minus b over c square times x1 because x is written as x1. Okay. Now let us multiply by this factor IC to the terms inside this small bracket. So gamma is here at each, and ICT, IC times t, that is equal to x4. Okay. And again, the second term will be multiplied by IC. So what will be that? That will be I, and one of the C will cancel out, and there will be V by C, and that V by C will be equal to beta. So this is minus I beta x1. This is fourth Lorentz transformation. Okay. So in terms of the fourth coordinate denoted by the symbol x4, which means ICT, you can write the four Lorentz transformation in this manner. Okay. Now the equations or these Lorentz transformations which you are seeing here may be written like this, which I have mentioned it here. You can see that x1 prime is equal to what? This is gamma times x1 plus plus I gamma beta x4. Okay. So you can see this result may be written like this: x1 prime equal to gamma times x1 and plus I beta gamma times x4. Actually, in that very equation, x2 and x3 coordinates are not present. But if our aim is to write x2 and x3 also in this equation, you can write like this. Simply multiply by 0 to x2 and x3. You can write this is 0x2 plus 0x3. Okay? Because after multiplying by 0, this will not make any difference in the result. So x1 prime can be written as gamma x1 plus 0x2 plus 0x3 plus I beta gamma x4. Okay. Now you have seen that x2 prime is simply equal to x2. But if you want to write x1, x2, x3 and x4 also in this transformation equation, then how we can write? You can easily see we can write x2 prime equal to 0 x1 because x1 is not present. As it is equal to x2, so we will write 1 times x2 plus 0 times x3 plus 0 times x4. We can write or not? Definitely. This is very easy concept. Now, the third Lorentz transformation you have learned, this is x3 prime equal to x3. Here neither x1 nor x2 nor x4 are present, but we will write all those terms. So x3 prime can be written as 0 times x1 plus 0 times x2 plus 1 times x3 plus 0 times x4. Okay. Now you have seen that what is this x4 prime? You have seen that x4 prime is equal to gamma times x4 minus I beta gamma x1. Just you have learned. Here x4 and x1 are present, but x2 and x3 are not present. So we will simply multiply x3 and x4 by 0 and add in this equation. So you can write this x4 prime equal to, see here, gamma times minus here there will be not gamma because gamma has been taken as a common factor. Okay. So here there will be no gamma. This will be actually I beta, okay, x1, I beta x1, okay. So x4 prime can be written as minus I beta gamma x1 plus 0 times x2 plus 0 times x3 plus gamma times x4. You can see it here, okay. And in the light of this equation, you can easily write the Lorentz transformations in matrix form. And in matrix form, it will be very easier to remember the Lorentz transformation when we use the fourth coordinate by the symbol x4. Okay. So these equations, these four equations in matrix form can be written like this. We write a column matrix x1 prime, x2 prime, x3 prime, x4 prime. You can see it here. And there will be a 4 by 4 matrix gamma 0 1 I beta gamma 0 1 0 0 0 0 1 0 minus I beta gamma 0 0 gamma and times another column matrix. This is x1 x2 x3 x4. You can easily check if you want to write this x1 prime. What will be that? That will be gamma times x1. You can see this is your first term here, plus 0 times x2, this is your second term, plus 0 times x3, this is your third term, you can see, and I beta gamma times x4, this is your fourth term. So you can express all these four equations which are actually Lorentz transformations in this matrix form. Okay. Actually, this 4 by 4 matrix defined here is called a transformation matrix. When we apply this transformation matrix on the on this column matrix x1, x2, x3, x4, we get the event in the another coordinate system S prime defined by this column matrix x1 prime, x2 prime, x3 prime and x4 prime. So this 4 by 4 matrix is called a transformation matrix. Okay, and this transformation matrix is denoted by this symbol alpha mu nu. You can see it here. Actually, all those equations defined in this matrix form or here, we can write in a very compact manner. We can write that x prime mu equal to alpha mu nu times x nu, where actually mu runs from 1 to 4 and nu also runs from 1 to 4. Actually, I have mentioned here that Einstein's summation convention is implied here. Actually, you can see this x prime mu is written, can be written like this. This is summation alpha mu nu times x nu, where nu is equal to 1 to 4. But I have not written here the sign of summation. This sigma has not been written because this is just Einstein's convention. According to Einstein's summation convention, without writing the sign of summation, you can understand that summation is implied with respect to the index which is repeated in the expression. You have learnt this idea, Einstein's summation convention, in mathematical physics on tensor analysis. If you have not an idea of Einstein's summation convention, you can watch my video in the playlist of mathematical physics on tensor analysis, where you will find this a video on this Einstein summation convention. And this transformation matrix, you know, this is a 4 by 4 matrix defined by this. Now you can check how we can evaluate any equation from this equation B. As you can see that if we want to find any component, let us say your aim is to find x1 prime by using this equation B. How you can actually find it? As summation is implied for nu, so we will write alpha mu 1 plus alpha mu 2 plus alpha mu 3, and x1. Here will be x2. I am again writing here. Let us erase it because there was a mistake here. So let us erase it. Now see, alpha mu 1, first limit, and x1, nu is 1 here, plus alpha mu 2 x2, okay, plus alpha mu 3 x3, and plus alpha mu 4 x4. But as you have taken here mu equal to 1, it means in each term mu will be 1. So this will be alpha 11 x1 plus alpha 12 x2 plus alpha 13 x3 and plus alpha 14 x4. Now see, what is alpha 11? This is at the place of alpha 11. This is gamma. So we will write this is gamma times x1 plus alpha 12. This is alpha 12. This is 0. So this will be 0 times x2. Okay, plus alpha 1 3. Alpha 1 3, you can see this is also 0. 0 times x3. Okay, and plus alpha 1 4. This is alpha 1 4, and I am just underlining it here. This is I beta gamma times x4, and you can see this is nothing, this is simply this first equation. You can see this is your first equation, or from this matrix you can also find this. Okay, so in this way you can find any transformation equation from this equation B. So all those four transformation equations have been written here in a compact manner. You can use this sign of summation, or you cannot use this sign of summation. If nu is the repeated index according to Einstein's summation convention, already summation is implied for this index nu. Okay, so in this way we can write all the four Lorentz transformation equations. So I hope you have understand how the idea of four-dimensional space was developed by Minkowski, which is called, therefore that is called Minkowski's space, and what are Lorentz transformation equations. Actually, getting this idea of four-dimensional Minkowski space and the Lorentz transformation. Now, in the next lecture, we will see a very important concept of four vector. But I have already told you that I have already discussed this four vector in relativistic electrodynamics. But in relativistic electrodynamics, the examples of four vectors have been taken from the electrodynamics, that is current four vector, potential four vector, you have talked about. But here in the forthcoming lecture, we will see some new type of four vectors, like velocity four vector, acceleration four vector, momentum four vector, force four vector. Such four vectors will be described in very detail in the forthcoming lecture. Okay.